All right, test, or let's see. Well, let's get going. So use that as a fifth time. It kept failing. So you know what really makes me angry? When people skip class to study for other tests. That just infuriates me. Where's Eric? Eric? Oh yeah, there was somebody I was not supposed to mention. I won't mention him. It'll be nice. Let's see. Who else are we missing? There's Dane's missing, but he's traveling. And then there's another one that I'm not supposed to mention. I was asked not to mention because he doesn't want his name put out on the internet. Lito. Oh, whoops, I did mention his name. All right. Are there any questions on anything? We ready to talk about, let's do a quick review of common source amplifiers, shall we? With current source loads. Oh, before we do that, does everybody see the homework? Is these problems, which you should be like, man, that was a great learning experience. And then everybody sees, whoops, the project, I've already assigned it. Yeah, let's see, when is it due? April 28th. When did I assign it?
Today.
Wow, that's like 6 weeks. Holy crap, that's a lot of time. But you know what? I bet you students still complain. He needs to assign the project earlier. Well, I didn't start on it till a week before it was due, but... All right, so does everybody see that? No. I'll make yours a gigahertz and you'll never be able to do it.
That's mean.
No, I want to see what you come up with. All right.
It's alright, no, it's unattainable, so no.
Yeah.
Alright, no pressure.
I think that's good to push students, assign projects they can't actually do and see how they perform. The stress. All right, let's do a quick review. Let's do the following. I'm going to do this a little different. Where does that come from? Or a gate drain connected transistor, right? Yeah. And let's just assume AC circuit. And let's quickly find a gain. So how do I start? Holy crap, I feel bad even asking you this. What is that?
Find V out over VM.
Yeah, but what do I start? I assume when we said gain, that was V out over VM, but how do I start?
You have to find your GM with the RL.
You guys are, man, I'm like, my thought process is like, VGS is VN, so the current that flows there is GMVN. Super easy, right? Then the output resistance here is? And then what flows in these two resistors? I just asked you, here's a resistor, R, current's flowing backwards like this, that current's GMVN. So that gain is V out over V in is minus GM R out N in parallel with R out P. Okay, that should have bored you to tears if you're paying attention in class. If it didn't, you're not reading the book. You're not reading the book, you don't make it through the class. You don't review the videos, you don't make it through the class. Any questions? Easy? Yes?
It's March 17th and it's lecture 17. I just noticed that.
Yeah, I did
And it's
too.
St. Patrick's Day.
Today's St. Patrick's Day?
Nice green.
Do they still pinch? That's probably not politically correct anymore. If you don't wear green, you get pinched.
I don't know. That's what I was.
People still do it? Oh, okay.
I think so.
All right, I'm not getting pinched today, huh? Okay, so I'm going to do this is what kind of amplifier? Common source. Is everybody cool with that? So now let's do common gate. And I'm going to do exactly the same way. I'm going to do it twice. I'm going to do it 3 times. You're all going to help me. AC circuit. Let's do the AC circuit. What's the AC voltage here? Yeah, it's a DC voltage. I can't move it. It's AC 0. What's the DC voltage here? Yeah, it's a big capacitor. It holds it at AC ground. Is it DC 0 volts there? No. These two voltages are the same. So whatever current this supplies, this NMOS will go and bias and sync that current so it biases up correctly. But big means big compared to the output resistance. Okay, so this is 0. What is this voltage? There's a voltage source to ground. So what is VGS? Does everybody agree with that? 0 minus Vin is VGS. What's the current that flows in the transistor? GM times VGS, which is GM times minus Vn. What is the resistance due to this PMOS? And due to the NMOS, what's the DC voltage here? 0. Well, R out in. Is everybody cool with that? Now you could argue, well, doesn't it go to here? Yes. Is there really any difference between connecting it to ground and going to here? No, because V out's going to be moving by 300. This will be moving by 1. So for all intents and purposes, we can think of this as going to ground. However, if you want to be more exact, you can tie it here and do the analysis that way. We're not going to for this first time. So what is V out equal to? Yeah, GM minus GM times Vn times R out N in parallel with R out P, or V out over Vn equals GM R out N in parallel with R out P. Remember? So let's think about that intuitively. So it's positive. Common source was negative. So here's the input, plus minus, and here's the output. This is AC ground, plus minus. So the drain is common with the input and the output. So if I drive this voltage up, what does it do to this transistor? If I drive the source up with the gate at a fixed potential, what does it do to the transistor? Turns it off. If it turns it off, what happens to this node? That's a current source. It just starts going up. So if the input goes up, the output goes up. Does everybody see that? The gain's positive.
So the common source was just the input without
The input was here though. Yeah, so if the input went up here, then this would turn this one on and pull the output down. Does everybody see how I use the same topology? I'm going to change this now and draw it differently on the next page just to confuse you. Yay? Any questions? I got a question. Suppose I had a capacitor here, let's just call it C load. And I pulse this really high so that this shut off. Let's say the current flowing through there's I bias. What does the output voltage look like and why? So I drove this up, shut this transistor off, and now I have my I bias charging which is a constant current charging CL. Yeah, it goes up to VDD. What does the waveform look like? Okay, this is a trick. A lot of times when you interview, they will ask you circuits like this that underlie very fundamental concepts. The concept that we have right now is this. If I have a constant bias and you're charging a capacitive load, what does the output look like? I equals C dV dt. I is constant, CL is constant, so I over C is a constant. That's equal to dV dt. When is dV dt a constant?
By time period.
Okay, no. When it's a constant is when it's a ramp. Right? You take the derivative of a ramp, you get a constant number, right? Think of this more simply. If I have a constant amount of water filling up a bucket, what happens to the water level in the bucket? Just rises linearly with time. That's all the depth is. If you can answer that question, here's a complicated circuit. They say, oh, this shuts off. I got a constant current. It's charging a capacitor. What does the output look like? If you can get to the point where you're not saying you're losing the trees for the forest or the forest for the trees and say, oh, it's just a constant current. That's what this is, charging a capacitor and it's a ramp. Then you do well and you get the offer. You can't see that and you're like, oh, I don't know, I take the derivative and all this other nonsense. They're going to be like, I don't want that person. They're not seeing what's going on. Does everybody follow that? Okay, so let's go do another. So this is this is called slew rate, and we'll talk about this later in the semester. It's on your project. Slew rate needs to be greater than 100 volts per microsecond, which is 100 millivolts per nanosecond. Well, that says how much current do I need in my output to drive a specific capacitive load? Okay, I'm going to redraw the same circuit. And I'm going to do the biasing a little bit different. Should we have a quiz today? Yes? Maybe.
Well, you usually keep it out, so I don't think you're going to give us a quiz.
You don't?
Well, you usually bring one, like a packet, like at your quiz.
It's not in there?
I don't know.
Lido requested that we didn't have a quiz
Pretty
today?
consistent, though.
Well, Lido, oh wait, he said not to mention his name, so I won't mention Lido's name again. Let's just do this, 20 microamps. You know what's good? Ignoring me. He thinks he's funny. All right. Okay. So let's do this. 30 by 2, 10 by 2, big. And let's calculate the gain of this. Let's say V in is 1 millivolt, and let's look at the output, then let's sim it. Sound good? Okay, so this is a super easy problem. Just ask me. Tell me what this voltage is here, DC. Okay, this is from table 9.1, right? And I'm going to go ahead and cheat and make the body connection here, because if I don't, that'll forward bias the N plus to P diode. So I'm going to make the body connection like that. And if you don't understand that, look at the cross-sectional view of the device. Look at the body being grounded, and look at the N plus here being at a negative potential. How do I know this is at a negative potential? What is the source to gate voltage here from table 9.1? That's right, 1.05 volts. What is the source to gate voltage here from table 9.1? Oh wait, I don't know because, oh wait, I do know. What is it? That's right, 1.15. So what is this DC voltage? 3.85. We're going to verify all these. If you don't believe me, we'll see. How much DC current flows through that big resistor? Yeah, none. Okay, what's the current that flows in these two devices? 20 was the table 9.1, right?
Yeah.
Okay. And what's the current that flows in this device? Boom. Let's do the DC first and see. Minus 1.05, 3.85, etc. So, today's St. Patrick's Day, huh? Pretty nice. I remember while I'm doing this, when I was department head, about 2004 time frame, I went to a conference in New Orleans at this time of the year, and I took my kids there with me, and it was on St. Patrick's Day, and it was before Katrina, and holy crap. It was something else. And I remember walking down the street and having two young guys elbow one another and go, "Did your parents ever take you to a place like this when you were a kid?" And I kept thinking to myself, what did I do? Yeah, on Bourbon Street, yeah. It was funny.
Always interesting people there.
Yeah.
It's like downtown.
Yep.
Except older.
Yeah. All that changed a year later. They had the massive flooding. Okay. I'm drawing it just to be the same. And let's see. Control R. Question?
Yeah, can you explain again what's the big resistor doing there? Like,
It's just simply providing a short for DC. So the question is, what is the big resistor doing? It's a short. It's a wire for DC. But for AC, it's an open.
so there's no voltage drop.
Not for DC. So I could also use a large inductor. It would do the same exact thing. It would short for DC and be an open for AC. Good question. Okay. Let's do this. And we need a little AC joltage here. Yeah, joltage. And then we need a big capacitor, so let's go ahead and copy. And then we need a big resistor, so let's make that 100 MEG. Let's flip that. And let's see, we need to do one other thing. Oh, let's make a mistake. Let's show this goes to 0.7 volts when we don't connect the body over here, just as an error. So let's do a .op. hit save, hit run, and then we'll go over here, and we see that that diode is forward biasing. Does everybody see it's at minus 0.553? It's not at minus 1.05 as the VGS would estimate, or that we estimated. Does everybody see that? Does everybody understand why? So what is this terminal connected to in this cross-sectional view? N plus or P plus? Yeah, N plus. And what's this one connected to? P plus. So it forward biases that terminal. So we're going to fix that issue. That's not, I mean, if you don't follow that, that's not a hard concept. You need to understand there's a diode there. So we'll do this. We'll hit run. We'll do the same thing. And then now, if you look, it goes to minus 1.0665. Does everybody see that? VGS is just what it's right out of table 9.1. Then here, 3.85 volts. Why? VSG is 1.15. Here, 3.85, because zero current flows in there. The capacitor's an open. The resistor then has no place for the current to flow. Both sides are at the same potential. Any questions? So let's hit save, close this, go back and do the AC. So AC circuit. And what is this for AC? How much AC current flows in the DC current source? None. This is a short, so I have the following. Is everybody cool with that? I'm boring you, but I'm going to do it anyway. What do I replace the MOSFET with in my mind? Yeah, I'm repeating myself. What do I replace here? Going to ground. What is VGS? So what is that current? So it's pulled backwards through the two resistors, so V out equals minus V in, oops, which was equal to 330 last time I think we calculated. We ready to, any questions on that? It's too easy? Yes? It is? Good. All right. So let's go back here. File, save as, example 2. Is anybody using these files? No? Yeah. All right. Let's do decade, 100 points. Start frequency 1 hertz, stop frequency 10 kilohertz. Yeah, let's go. Let's start it. I'm going to show you an issue here. I'm starting at 1 hertz. Now, this capacitor's 1 farad, but the input resistance here is low. And it'll still be fine, but what is the input resistance? If I ask you, what's the input resistance of this amplifier? That's the resistance looking this way. Yes, 1 over GM. So let's prove it real quick before I do the example. Oh, the input resistance looking in, there's my eyeball. The input voltage is V in. When I apply a test voltage, the current that flows in Vm is GM V in. That's the resistance looking in, and that's 1 over GM. So everybody agree the current is GM V in, and the voltage here is V in? So it's 1 over GM. See how easy that was? What's the output resistance? I only ask easy questions. Does everybody agree with that? Okay, so now let's go back. Hit run. Let's look at our VN. Boom. I don't like dB. You know, I'm going to change this to 1 even though it's not small signal. Then I don't have to do the ratio. You know what? Let's do the ratio because that's good when you're learning. And we'll do boom, linear, 1 millivolt, output, boom, 110. I don't know why it's not 330 like we calculated. So I can do the gain as V in. And I can get the scissors out here. And hit save, and so my gain is 110. Just out of curiosity, I don't think this matters, but it's mega ohms versus 100 megs. So let's see if there's any difference. Yeah, teeny bit. All right, any questions on that? Can I do a DC sweep with V in here? And look at V out? No, why? Capacitor's an open for DC. Can I remove the capacitor and do a DC sweep? Well, I could, but what's the issue? If I remove the capacitor, this is shorted to ground. So this is connected to ground, this is connected to ground, so all of this current will flow in the ground. So if I remove this capacitor, it shorts this node to ground. Does everybody follow that?
You have a voltage source there?
Yeah.
What's the difference between that and the voltage source up
Here? This one's supplying power to the overall circuit. This one's not.
there? But if you, what would you be sweeping?
Here, let's do this. Let's do save, save, let's close that. Let's go back and open that, and then let's do file, save as, example 3. Or actually, you know what? Let's open the other one. That one's easier because I don't have to change the analysis. Let's do file.
Just go through where that line
Let's find out.
source is not gonna make it to the.
Let's even find out. Let's see if that old Dr. Baker knows what he's talking about or he's full of it. Okay, so let's hit run. What's the DC voltage here? What's the DC voltage here? Of course it's 0. I've got a 0 volt DC supply connected to that node.
I thought you said you were gonna sweep it.
What do you mean? Can I sweep it? Means if I sweep it, it will, if I go negative, if I sweep positive, it'll work, but if I sweep it, I can get it where it'll work as long as I go from like -2 to -1.
That's what your original question was if you swept.
I
You took
sweep
that
it.
capacitor out and swept the.
No, I said if I sweep it, the first question was with the capacitor. You'll need to review the tape or the video, whatever they call it nowadays. And then I said, well, what happens if we take out the capacitor? And the answer is it won't bias up correctly.
If you sweep it without.
I didn't say if I sweep it. I said, what if I remove the capacitor? If I remove the capacitor, this is grounded, right?
But you assume that you're removing the capacitor and the continuance of your original question.
Ah, okay. All right.
That's
I'm
why I was
unclear. See,
confused.
poor instruction.
Obviously, if it's 0 volts, it's gonna just be.
Okay, and then I said the 20 microamps will flow in here, so let's see what flows in there. Boom! 20 microamps. Why is it negative? Spice defines positive current flow as plus to minus. In this direction, the current would go like this. This is stuff you learned in Circuits 1, right? Right? Any questions? This doesn't work. Let's go ahead and do a quick edit. Text. Yes.
I think I have issue on that animals.
This one?
Yes.
You have issues with it?
Yeah, technically we are connected to the body to the ground, and then I know you first one when this capacitor is connected to ground. That means the NMOS connects the
Oh.
TMOS, T class, or
Wait,
that's very confusing me.
all I'm saying, this is like a discrete MOSFET. In a discrete MOSFET that you go get in the lab, the source and body are tied together. Don't think any deeper than that. For our process, we can't do this. But for a discrete MOSFET, we can. Yeah. All right, let's go and now look at one more example of common gate, and then we'll move on to common drain. How's the pain? We want spring break to start. Why? Can't you be nice and let us go early and cheat us? No. All right, so let's do the following. I'm going to make a mistake, and you're going to tell me what the mistake is. What's the mistake here?
Don't you need a resistor without a capacitor, so you have a DC?
Where?
Well, there's no AC.
Yeah, AC's right here. Yeah, big capacitor, so it looks like a short. Yeah, it's a short, right? This is, AC is 0. It's holding this node fixed. You can't move it. So if I try to apply an AC signal, there's no way any current's going to go here because the AC voltage is 0. So all I would get is a huge current that flows, limited by the capacitor. I can't do this. Does everybody follow that? The AC short, I can't move this node. Any AC current I have will go directly to the DC supply because it's fixed. Can't wiggle that node. It's a short. Looking good? Let's fix it. Does anybody not follow that? Okay.
You just put a resistor in there, right?
If I put a resistor in here, does it fix anything? If I put it right here or here? No.
Put it before that node.
If I put it here? But then I mess up the biasing of this, right? Because I need a source gate voltage which is set by a gate drain connected transistor. Yay or nay? All right. So let's do the following. What kind of amplifier is this? So what is the AC voltage there? What is the AC voltage there? Big capacitor says don't move. I got a big capacity here. What's the AC voltage here? labeled V out. I mean, it's already there. What's the AC voltage there? What is VGS? Gee, he's repeating himself. How much current flows? Oh, yeah. Yes, thank you. Oh, whoops, I got it flowing the wrong way. Right, flows from the source to the drain. Looking good? Oh, yeah, positive Ian, thank you. Because that's AC ground. And what's the total resistance on the output node? What? It's ROP in parallel with RON. Right? So what is V out equal to? Box around the answer, 100% credit. Easy to grade. Did you come in, Co, for the quiz? That's not good, man. You have a test pretty soon? All right. Any questions on that? Oh, I want to know what's a common gate? Why is it common gate? Common. There's the common AC gate. There's the V in. There's the V out. Any questions? Because I'm going to move on to common drain, which is our last amplifier topology.
So, because you know the one that is in common, right? Because obviously it's either one of the transistors, right?
Yep.
Is it whichever one
Is
the
amplifying. Yeah.
Okay.
So this, the V in, is going to the amplifying device.
Okay.
So this is the load.
Oh, and then the other one, the top one was the load.
Yeah, the top was the load, and the amplifying device was the NMOS.
Okay.
Whichever one is not gate drain connected, right?
No, I could change it up. It's like that's the load, that's the load. You know what? Let's do one real quick where I don't have a gate.
Is it pretty much like whichever one is not treated as just the R out?
Wait, didn't I do?
Generally, that's the one that
Yeah. Oh no, the first one I did. Here the load is this one,
Right.
right? That's the load, and then this is the amplifying device. Yeah, this is the current mirror load. All right. So let me just real briefly, so you can answer this. Why would you want a common gate amplifier or a common source? And both have the same gain, right? Voltage gain.
One would be negative, one would be positive.
Well, one's positive, one's negative. But let me give you another example. This is something that confused me when I was learning. I'm like, why, if I look at the common source amplifier here, the input impedance is infinite, right? Does everybody see that? So it's high. I want high input impedance. If I look at the common gate, the input impedance is 1 over GM. It's low. So one has a high input impedance, one has a low input impedance. And let me just tell you, and then I'll prove it to you right now, for a voltage amplifier, you want the input impedance to be infinite. For a current input, you want the input impedance to be 0. And let me explain that to you right now. So say I have a voltage source here, and that voltage source called Vn has some source resistance. So let me explain that. When you look at a source, it can only supply some amount of current. Okay, say you're at your sprinkler timer, and your sprinkler timer is going to go turn on the solenoid and turn your sprinklers on. Well, it can only supply some maximum amount of current, and so the voltage divided by the maximum amount of current basically gives you the source resistance. So you can't turn on, you can't supply an infinite amount of current. Does everybody follow that? So you would say, what's the open circuit voltage I can supply? What's the short circuit current I can supply? Then I get, this is my source resistance. And you might have a really weak driver, especially with time, it starts to die. Well, if you go into a voltage amplifier, and this is your input impedance, Rn, for a voltage amp, so this would be Vn, let's call this in V source. What do you want Rn to be in order to maximize Vn for a voltage amp? You want it to be big, right? Because if it's big, then all of the source is equal to the input, and I don't have to supply much current. Does everybody follow that? So for a voltage amplifier, you want large input impedance. What about a current amplifier? So here's a current amplifier. I got a current, I source, and there's some source resistance, and then you have some input resistance, Rn. I want my Rn to be 0, because then all of my R source goes over to here.
It's like when you do your voltage divider
Or the current divider. You want this to be, so this would be a current amplifier. So if I'm doing a current amplifier, I would want to use like a common gate where I would have low source impedance, right? Or low input impedance, so all of my source. Now let me give you an example of this, because this also confused me. I have no problem thinking about voltage amplification, because I have a stereo, I have an audio system, I can take the two left and right plugs and I can think of it as a voltage. Where do I think of a current source? A simple example is in your remote control. In your remote control in the TV you're pointing at, there's a photodiode, and it's reverse biased. And if you look at the curve of the photodiode, it looks something like this, which we know is modeled as a current source in parallel with a resistor. So when I take and I point my remote control at the diode in my TV or whatever I'm controlling, the light hits the diode and it generates a current. That's the infrared. You can't see it. I remember when my kids were young, they used to have these tag laser game, the little laser guns that they would run around and shoot each other with, the little thing they would wear around their chest to try to laser tag. And I would get my remote controls, and I would shoot them with my remote controls. They didn't like that, right? Because I'm not wearing a tag. I'm like, you guys get out of the way, I'm going to shoot you. And then I'd shoot them with my remotes and set off their little laser tags. Anyway, it was good times. Anyway, if you hit the laser with your infrared there, it generates light. You don't want all that. You want the light there to go into your amplifier. And so that's why they want it to be very sensitive. You can actually set it to point at the ceiling sometimes, and it'll bounce off the ceiling and go down to the receiver and be picked up by the receiver, because they're super sensitive, because they designed for the lowest noise possible. So your battery starts to die. You aren't sending out much light. It still works. Okay, this is an example of where you would need a low input impedance. Does everybody follow that? Okay, the last topology we're going to discuss is called the common drain or source follower topology. And it's used for high input impedance amplifiers where you get a current gain and the voltage gain is 1. So the voltage gain of a common source amplifier is basically 1, and it's used for presenting a very high impedance load. Okay, so this is called the common drain or source follower. And this is what this topology looks like. And why don't we do this a little bit different? I'm going to just put a resistor here called RL. I'm not going to worry about the biasing to begin with, and I'll do several examples. And V out. I know students hate examples, but I'm going to do them anyway. Why is this called common drain? Everybody's looking at me like, what the hell is he talking about? We love examples. Here's the drain. Yeah, with the in and the out. Okay, so let me give you an example of where this is used. And we're going to talk more about this when we come back from spring break, but you're going to have read about this all in Chapter 1, Miller effect and the capacitors and all that, right? if this node goes up, what does it do to this transistor? Does it turn it on or off? On. So what does the output do? If it turns on, what does the... Okay.
It took all the capacitors.
It was like a black screen.
All right. What does the output do if I turn this transistor on? Goes up. I'm turning the valve on, more water flows, the pressure goes up here. I'm not thinking deep because this is all easy stuff I learned when I was playing around with a hose and a bucket when I was a little kid. Okay, righto. Okay, so if it goes up, now imagine I've got a capacitance here, which I'm going to call CGS. If both sides of the capacitance go up at the same amount, how much current goes into this capacitor? Nothing, right? So where is an example of a source follower used? When you have your phones and you take a picture with the CMOS image sensor that's in the phone, there's a photodiode in there, and above that photodiode is a red, green, or blue color filter. The light goes through the color filter, and that's how you get red, green, or blue when you do a color image. It hits the photodiode, and just like we said before, generates carriers that cause this capacitor to, it actually discharges because it's pre-charged high. So it discharges the capacitor, and then the more it discharges, the brighter the image. The less it discharges, the darker the image. Okay? The longer you let it integrate, the more you can build up signal, and that's how you can get images in dark environments as you integrate longer. You let the exposure to the photodiode go. Now, the first amplifier stage when reading out the pixel in your CMOS image sensor is a source follower. Because when you take a switch and you transfer that charge over to the source follower, the input capacitance is very small because both sides go up at the same rate. So you take this teeny little bucket here and you transfer the charge or the water into another bucket. You want that other bucket to be as small as possible so you get the largest signal there. Okay, so this is one example. You have millions of source followers and other amplifiers on you right now. This is one example of where this amplifier is used. Okay, now let's go and do a, well here, let's do the analysis of the gain right now. What is this AC voltage? What is this AC voltage? What is VGS equal to? Right on, V in minus V out. So what is ID equal to? GM VGS. And what is V out equal to in terms of ID?
Let's be it.
Well, let's be more complete, right? Does everybody agree with that? ID flows in RL, so ID times RL. All right, so V out equals RL times GM times V in minus V out, or V out over V in equals GM RL over 1 plus GM RL, or let's write it a different way, RL over 1 over GM plus RL. Does everybody agree with that? Too slow? What's the impedance I see looking back in there? 1 over GM. In parallel with R out in, we'll neglect R out in. Impedance looking back into the source is 1 over GM, neglecting R out. Impedance to ground is RL. This node voltage is? What is the label of that voltage? V out. So I got a voltage divider between RL and 1 over GM. So V out is equal to V in times RL divided by RL plus 1 over GM. Exactly what I just derived. Questions? Let's do it again. Let's use, and then we'll do a simulation. Seem challenging? We'll see on the quiz. What's that?
It's on Tuesday.
When we come back. I'm too nice, aren't I? Let's do this problem. We'll call this V common mode, whatever that voltage is. What is connected here? Yeah, gate drain connected NMOS, or the beta multiplier, which has a gate drain connected NMOS. Okay, I want to ask first question, what is the minimum value of VCM? Does everybody agree with that? This circuit doesn't work unless I raise this voltage above VGS plus VDS sat. How? Because VGS is VDS sat plus V threshold in. Just repeating himself over and over again. Does everybody agree with that? Does everybody see how I got to raise this voltage up enough to turn this on and to apply a potential across here? So let's say this is a 10 by 2 and this is a 10 by 2. What is the current that flows in there? Yay? What is this voltage? Boring, eh? What is this voltage? Neglecting the body effect of this one. So what is the DC voltage there? I gotta have that DC voltage there or it won't turn on. Is everybody cool with that? What's that? Yeah, this is, what's the DC voltage there? I assume. Right? And then VGS. Any questions? Okay, so let's write the AC circuit. What can I replace this with for the AC circuit? Of what value? And then what about this one? It's also got an RON, right? How about I write RON in parallel with RON, which is RON? Yeah. And then what is this voltage here? And what is VGS equal to? And what is V out equal to? And what is ID equal to? V common minus, no, that's the DC. This is AC. And this is, okay, V in minus V out. And so once again we get V out over V in is equal to GM times R out over 2 divided by 1 plus GM R out over 2. which is approximately, assuming GMR out, what is this approximately equal to if GMR out over 2 is big? 1. Input comes in, output goes up.
Is that kind of like in the recent homework, that third one that we did? With
I don't know. All right, questions? Let's do a sim. Okay, wait. First off, I say V out over V in is equal to 1. Does that mean the absolute value of V in and the absolute value of V out are going to be the same? No, they're going to be shifted by a voltage, right? The VGS, right? So let's do that. Now, I want to have a good spring break, so after today, I'm going to go do the homework and get it over with. What the heck's going on here? Okay. Yeah, I don't like that one. Yeah. Alright. File, save as. So I want to put a BMR in here and use that. Tell me how to do that. Grab this one. No. Grab this. Go to this little arrow here and go to the directory. Then figure 2022. And let me just make sure that's the short channel. So let's do this. Yeah, we need to add that. So let's hit save, boom. And then let's go over here. 2022. Let's go into LT Spice. Chapter 20. Oh, you know what? Let's do 43 through 47. Control C. Let's come over here. Control V. And let's get rid of these for now, because we already have them in 47. Then let's go back over here. Open that up. Go back here. 43. Holy crap.
2015 is
No, the one we're going to use for everything. Whoops. That's got so many bias voltages we can do anything. So then I'll press G. And I'll get my little scissors out here. And then I'll get my label maker here. Go over here. Put a label there. Put a label there. Put a label there. Move this out of the way. And then I'm going to get my scissors out again. I'm going to leave this in so I don't have to put another PMOS. So let's just go ahead and move this out of the way, and I won't do anything with it except hit fit, and then let's just wire everything together. I don't think it'll complain if I don't wire them, so let's just leave it like that. Get over here. Goodbye. 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 Okay, so let's grab this. See, if I did PowerPoint, these would already be made up. That would be good. We could cover so much. What am I going to connect this bottom NMOS to? And let's make a little wire here. We're almost there. Oops. Let's find out. V bias 1. There it is. Source gate right there for PMOS. V bias 4. There it is. Gate source for the NMOS. And I know these bias circuits because they're going to be on the final exam. He's going to ask me questions like, what's V low? What is V low? VDS-SAT. Alright, copy. Are we good to go? Questions? What's that? What's that? Oh, yeah. How about let's do this. For the first one, let's do a DC sweep. Let's do V1. Whoops. V1 from, how about 0 to 5 in 1 millivolt steps. Okay, when it's at 0, what's the output going to be? Tell me what the output's going to be when I look at this. No, if the input's 0, what's the state of this transistor? It's off. So the output's going to be pulled to ground through the current source. In fact, nothing interesting is going to happen until this gets to about 1.1 volts. Then this will turn on and the output will start to go up. What's the maximum this can get to? Right, so this node, it's VDD minus VDS-SAT. This node can actually go above VDD and it'll still work. But let's see what happens when we just plot input versus output. Ground on VDD. Where? No. This doesn't do anything. I just left this here so when I do another schematic I have a PMOS and I don't have to re-enter anything. I can get rid of this. Let's get rid of it. I don't want to confuse anybody. So let's hit run and V in. Boom, there's V in. Then V out. There's V out. Notice V out is at a lower voltage than V in because it's level shifted by this value here. Okay, does everybody see that? Notice that I can actually keep going up with my input. Source followers can actually go beyond the power supply rails then, both PMOS and NMOS. The NMOS can go above VDD and the NMOS can go below ground, so they're useful for level shifting. Okay, so let's do this. Let's do 7. Boom. Run. And then of course at 5 volts, close to 5 volts or VDD minus 5 VDS-SAT, it starts to level off. Does everybody see that?
So it'll just gradually kind of creep up, but it'll more taper.
Yeah, so once you get where the devices stop being in saturation and it goes into triode, it behaves like a resistor and it kind of just slowly goes up. Yep, alright, so let's do this now. Let's do the AC gain. Tell me what a reasonable value for the DC voltage here is based upon what you see here. How about 2 volts? 2 volts would bias me right there, right? So let's go close all this. Watch these disappear. Go to File, Save As, Example 5. Then go here. Have you had any of your classes canceled today? What? Really?
450, we're still waiting to get email.
I am sure it'll be held today. That's important stuff. Okay, so let's go to AC, decade, number of points per decade, 100. Start frequency, 1. Stop frequency, 1 kilohertz. Okay. There, it's going to be slightly less than 1. Let's see what happens. It'll be like 0.8, I would guess, because of the body effect. So let's plot V in, 60 dB, left click, linear, boom. And let's plot V out, boom. Notice the AC doesn't show the DC, but you see, why is that coming up with a different color? Let's put something that's easy to see. And you notice that if we were to make it a little bigger, like we go, bottom is 0, top is 2 millivolts, tick is 0.25 millivolts, boom, then you can see the difference. Now, what I'm going to cover one last thing here, which is why isn't it closer to 1 as we derived? Okay? And the reason is because of the body effect. So I'm going to show you what that means in just a sec. But does everybody, if somebody asks you, what is the benefit of a source follower? Your answer is, its voltage gain is 1, but it has a current gain. Meaning that how much current does this input supply? Basically 0, right? I mean, there'll be a little bit, but 0 inputting current because it's going into the gate of a MOSFET, which is a high impedance. So it's great in like charge amplification where you don't have much current or you don't have much charge to amplify, okay? If I ask what is the output impedance, it's roughly 1 over GM because when I look back in here I see a 1 over GM looking up in there. So it has a low output impedance. Okay, so let me save this. Let's hit save, save. Then go back here and I want to show you something. If I go now, remember we were at 0.82? If I do a save as and I go to example 6 and I hit save and I go here and I come down and then I go save and then I hit run and I plot my input and my output. Oops. Does everybody see there basically the gain is now much closer to 1 like I derived? And the reason is because I neglected the body effect. So I want to briefly cover that. Any questions? Okay, so before I do that, what is the body effect? He keeps saying that. What is the body effect? So the body effect is the following. If I look at this transistor, whoops, that way I can get fewer questions. If I look at this transistor, no body effect, because the source to bulk equals 0. Does everybody see that? So when I plot ID versus VGS, I get a curve that looks like this. If I go this configuration, so this is my bulk, this is my source. Now source to bulk voltage may not be equal, it could be, but it may not be equal to 0. If the source to bulk voltage is non-zero, my curve, this is for VSB equal to 0, my threshold voltage goes up. So the larger my source to bulk voltage, the threshold voltage goes up. That's body effect. So whenever I say that term in your mind, you should be thinking, oh, all that means is source and bulk aren't tied together, so the threshold voltage goes up. So now if I have an AC voltage here, like I have with the source follower, and that's V out, I start to modulate or change the threshold voltage, which then causes a current to flow, which is, we model as GMB VSB, where the source to bulk voltage is here. So, what if I look at that, and I look at what I'm going to read in the book here, because I read the book, because the book's really, really easy to read. And I look at the source follower. Oh yeah, frequency response. Make sure you read that. That'll be good times. If I look on page 601, if you look at the top, whoops, mechanical failures of my dock cam. 601 or 691, my vision's failing. If I look there, you see this is the equation we derived. All right. If I go include the body effect, I have this extra transconductance here. So when I go derive the gain, it ends up being this 1 over 1 plus eta here, and that's less than 1. And so for most practical source followers, the gain is set by the body effect, not by the output resistances. So make sure you're gurus with chapter 21, and if you get bored, read chapter 22 as well. Okay? Have a good spring break. We'll see you in about 10 days.